Hey everyone, welcome to part 2, finding optimal parameters to model total cases with scipys least squares function. So here's our function that we just used in the previous video to look at exponential growth and decline. In this section, we're going to try to find the best values for A and B such that the curve that this makes will look very similar to the coronavirus cases of a particular area. So we're going to use the state of Texas from the beginning all the way through September 1st. So let's go ahead and grab our data. We will remove any days before there was the first case, and that's what this line does right here. This is easier to see when we plot it. So we're going to have data from the beginning of March all the way to September 1st. And what we want to do is find the parameters A and B so that the curve will look as similar as possible to this curve right here. So you'll notice that there was little growth in the beginning. It looked actually quite steady and linear, and then there was a big exponential growth over here in June and July. So let's go ahead and see how we will do this. The first thing we'll do is we'll create a function that takes in the x value and the parameters A and B, and all it does is just output the value of the function. So we'll call this simple exp, and what we'll do is try to optimize, right? Try to figure out the A and B such that the curve is as close as possible to this one over here. Now you could do this manually. You could just keep guessing A and B and look at the graph and try to do it that way. That takes a long time, so we'll do an automated procedure with the least squares function in the scipy.optimize module. So to do this is a little tricky at first. It takes some effort, and we're going to cover that right now. So to get started, you have to create another function called optimize func. You can call it whatever you want, but that's what it's called here. And what this will do is, the main thing is that it returns the error between your model and the actual values. And what it does is it takes the parameters for the module as a tuple. So this will be A and B. It'll take the time, X, the actual data, Y, the number of cases in this case, and then your model, which will just be this function over here, that exponential function. And what it does is very simple. It just calculates the value of the model. So it just passes it to that previous function, the X and the parameters. It'll get the prediction, and then it'll calculate the error, and then it will return the error. So that's what that does. Now, how least squares work, and we need to make sure we have executed these. How least squares works is that you have to, here, take a look at this bottom line is probably the best way to look at it at first. So it'll take all of these inputs. It's going to take this optimized func, which we just defined up here. So this is a function that has to return the error. And then you have to give it an initial guess for the parameters as a tuple. So if you take a look over here, the initial guess is just 1 and 1. So we'll guess 1 for A and 1 for B. And then the arguments this args will be passed to the optimized func. So we're going to give the optimized func our data, X and Y, and the actual model over here, simple exp. And then the last thing we'll do is give boundaries for the parameters. So the optimization routine knows where to look, right? So we don't want to look in the entire space. We want to bound the space that it looks at. And the way you do it is a little tricky. You're going to give it a tuple of lower bounds and upper bounds. So the lower bounds, they map to A and B. They're a tuple, so 1, 1. It's the same as our initial guess. So coronavirus cases do start at 0, but if you allow A to be 0, then there will be, it'll just be, the value of the function will just be 0. So we'll just make that 1 as the lower bound, and certainly not negative. And the lower bound for B, well, this should be 1 as well, because, or else it wouldn't be exponential growth. It would be exponential decline, and we cannot, we're modeling total cases, so there'll never be a decline here. So this is going to be the minimum. And then the upper bounds, and this is for A, we're going to make infinity for a, so the cases could potentially just keep going on and on forever. So we'll just leave that as a very high number. We won't try to estimate an upper bound for the total number of cases just yet. And then we'll have a growth rate of 10, which is very high. We saw that a growth rate of just 10%, which is just 0.1, would lead to very fast growth. So this should be high enough to capture the correct growth rate. And then what we do is just run this cell, and it'll return some object. And we'll go into this object in just a bit. So let's go run this, and it happened quickly. And sometimes the optimization routine can take quite a long time, but we have such a simple function, just 2 parameters, that I was able to find the lowest, the best parameters very quickly. And what it does is it attempts to find the least squares. So it finds the square of the error, and it sums up all of those errors, and it attempts to find the values of A and B that produce the least, squared error. And if you look at this object over here, it has a lot of different values. So it has like the cost at each iteration, and a lot of different data from the optimization routine. We're not going to go into that right now, but you can examine those on your own. What's important right now is the values of the parameters, and that's stored in the attribute x. So it gives it back as a NumPy array, and here we have A, that's what it found, and B over here. So A is exponential, or in scientific notation, so this is about 13,000 as a starting value. And then we can see that the growth rate, this is probably the most important piece, is that it found it to be 2.3%. So that's what it did in the optimization routine. And let's go ahead and look at both the model and the actual data in a plot here. And you can see the actual data is in blue and the model is in orange. And you can see it looks, sort of okay. It's following it, it's tracking it. There is this exponential decline or growth. So it looks pretty good. Now the biggest problem here is that, thankfully, cases are not just follow an exponential growth, or else they would go off to infinity. So we'll learn a different model that will be able to not grow off into infinity. But this is for a very simple model in the early stages of the growth phase of a coronavirus outbreak. Does okay for the the simplest possible model that we can build. Okay, so that's the whole procedure for using the least squares function to find the optimal parameter